Hello, today we're going to talk about the chain rule for differentiation of multivariate functions. To begin with, I want to go through this using a tree diagram in order to understand how things work when we're dealing with a chain rule and multivariate functions of multivariate functions. So when we draw a tree diagram, we're always going to start from the dependent variable and work our way down through the middle variables and all the way down to the independent variables. And on each branch, we're going to write the partial derivatives that we need to use. And then we'll come up with a representation for all the different forms of the chain rule. Okay. So first I want to start with how this works when we are working with a single variable version. When we had some situations where we had y is equal to f of x and x was equal to g of t, and we may have seen it written more as something like y equals f of g of t, something like that. And so we know that when we would take the derivative of this, we would get y prime, and it's going to be equal to f prime of the g of t, and then times g prime of t. And so that's how we handled that before. But if we draw that up in a tree diagram, when I talk about starting with the dependent variable, that means I'm starting with y. And then I have a branch that goes down to the intermediate variable. In this case, that's going to be x. And then I have another branch that goes all the way down to the independent variable t. Okay? So along the way from y to x, the derivative that I would calculate would be dy dx. And then along the way down to t, from x to t, I would be calculating the rate of change of x with respect to t, so dx dt. And so then if I want to write up what y prime looks like, y prime is actually going to be dy dx times dx dt, which is exactly what we had with the f prime of g of t times with g prime of t. Okay. Now, in the multivariable version, we have a couple of different cases. Well, the first case is where there's just one overall independent variable, and then the other case is when there is more than one independent variable overall. So we have to figure out, number one, how do we take a derivative and how many derivatives can we take? And the number of derivatives that we can take is going to boil down to how many independent variables we have. So this first problem, I'm working with z equals f of xy, x is equal to g of t, and y is equal to h of t. And I want to figure out how would I find, so how to find del z del t. I know it's going to be a del there because, well, z is a function of more than one variable. So how to find this? Well, let's see. I have to start with z. And then z is a function of x. So let me get the z on there. And it is a function of y. So z is the dependent variable, x and y are the intermediate variables, and then x itself is a function of t, and y itself is a function of t. So if I want to get derivatives, like the derivative of z with respect to t, then it looks like I'm going to have to go down two branches to do so. So from z to x, I would calculate del z del x. However, from x to t, now x is a function of one variable. That's it, not multiple variables. X is just g of t. That's what we see right here. So when we take the derivative of x with respect to t, it actually is just dx dt. The only time we use the del notation is if the function that we're working with is a function of more than one variable. Okay, So using that logic, if we go down the other branch from z to y, since z is a function of x and y, taking a derivative would require the del notation. So it's del z, del y. But going from y to t and taking a derivative, y is just a function of one variable. There's only one variable to think about. So we would be calculating dy dt. And then we would have to add our branches together to get our full del z, del t. So here's what that looks like. We are going to say del z, del t is equal to, okay, first we collect the first branch. The first branch says you're going to take the partial derivative of z with respect to x, and then we're going to multiply it by the full derivative of x with respect to t, dx dt. That is one branch. We need to add the second branch. The second branch says, in order to get down to t, taking derivatives, I have to start with del z, del y, and then I go from y to t and collect dy dt. So this is the full expression that we would have to calculate the parts for if we wanted to calculate del z, del t. Now, case 2 is, again, a multivariable version. However, notice that x and y are now both functions of two variables. So we've got a little bit more going on here. I'm going to create my tree diagram again. So I would have to start at z. Z is a function of two variables, x and y. And then x itself is a function also of two variables, s and t. And then y is a function of two variables, s and t. Okay, so if we want to find derivatives here, then what we have to do is first figure out what the derivatives are as we go down the tree diagram. I'm going to start on the left on the one branch from z to x. Since z is a function of two variables, any derivatives are partials, so I'd find del z, del x. Now, if I wanted to find the derivative of x with respect to s, I would have to actually be taking a partial derivative because x is a function of s and t. So that would be del x, del s. And on the flip side, if I wanted the derivative of x with respect to t, that would be del x, del t. Similarly, on the other branch, going from z to y, I would be finding a partial derivative of z with respect to y. And again, similarly, from y to s, since y is a function of s and t, these are partial derivatives, del y, del s. And then y to t gives me del y, del t. Let me write that again, del y, del t. Okay, so because there are two independent variables, that means we can find two derivatives. And those are del z, del s, and del z, del t. So s and t are the independent variables. X and y are the middle guys. They're the intermediate variables. And then z is our dependent variable. So if we look at del z, del s first, our goal is to travel down the branches and end up at s, okay? Not at t. We are not thinking about t here at all. We are only thinking about s, okay? And so we are still going to have this sum thing going on, but we're not going to be adding like four things together. We're only going to be adding together the branches that lead to s. So the first branch on the left, I travel from z to s, and as I do that, I go through del z, del x, times del x, del s. And that takes care of the left branch. Going to the right branch, I have to add. And so to get down to s, I will be using del z, del y, and multiply that by del y, del s. And that's it. That will give me my partial derivative of z with respect to s. Then I can do the same thing for del z, del t, del z, del t. Now I'm going to go down the branches that take me to t, not s. I am not thinking about s at all, only t. So to get there, I travel down the left branch first. Z to x to t will give me del z, del x, del x, del t, plus, and now I go down the right branch. I'm going from z to y to t. So it's del z, del y, times del y, del t. Okay, now some of you may be thinking like, hey, those del x's cancel out and those del y's cancel out, and that'll take care of some stuff. Don't do that. These are partial derivatives. We have to calculate them. So it'll, we're going to have actual functions. It won't just be z equals f of x, y. It's going to be like there are going to be functions there. And x is going to be a function and y is going to be a function. So we have to calculate all these derivatives and then pop them in. Okay? So let's, I guess the last thing to talk about is, in general, if we have a function u and it's a function of n variables, with each of those variables being a function of m variables, then, this should be ending at m, this should be ending at m, then we would say that u is a function of the innermost variables, the t's, okay? And then what this big old chain rule here is showing us is that we could have as many branches as we want, right? We could have as many intermediate variables and as many independent variables as we want. We should still be able to calculate our chain rules by going down the branches that lead us to the variables that we're interested in, okay? Fortunately, we're not going to focus on massive trees here. We're just going to focus on, 2 or 3 variables at a time. So let's just use these to guide us in calculating the chain rule, okay? Now, this first problem, we are asked to find dz dt. And I guess actually, you know what? Hold on. Let me just say that up here. When I was calculating, that was an error on my part. Because the innermost variable is t and there's only one innermost variable, we would be calculating dz dt. And over here, it would be dz dt. I'm sorry about that. But to get dz dt, we have to travel through some partial derivative branches. Okay, my mistake there. Okay, so now we want to find dz dt when z is equal to 4 minus x squared plus xy minus y squared, x is equal to 3t squared plus 1, and y is equal to sine of t. Okay, now dz dt, we learned we have to travel down the 2 branches, x and y. So down the x branch, leading us down to t, we would be taking a partial of z with respect to x, multiplying that with dx dt. Plus, we would take the partial of z with respect to y, so now I'm on the second branch, times dy dt. So this is just telling me all the parts that I need to calculate, okay? So I'm going to go ahead and calculate those pieces, and then I'll just pop them in. That's it, okay? So let's see, del z del x is equal to, if I look at my z function here, the derivative of 4 is 0. The derivative of negative x squared will give me a negative 2x with respect to x. The plus xy will leave me with plus y when that's the derivative with respect to x. And the minus y squared will be 0, okay? I should also calculate del z del y while I'm here. Running a del y through, the first 2 terms go to 0, 4 and minus x squared. Those are both constants. The derivative of xy with respect to y is x. The derivative of minus y squared with respect to y is minus 2y. So those are our two partial derivatives. Now I also need dx dt. X is 3t squared plus 1, so dx dt is just 6t. And then I need dy dt, and y is sine of t, so dy dt is just cosine of t. All right, so now we can go ahead and pop everything in. dz dt is del z del x, so in parentheses, I'm going to rewrite that as y minus 2x, just so I like my negative sign in the second term. That's the only reason. Times dx dt, which is 6t, plus del z del y is x minus 2y, times dy dt, that's cosine of t. That's it, we're done. That's all we have to do. Okay? There is no need for you to replace the x's and the y's with the functions of t, although you can. Okay? Technically, dz dt is telling you, hey, this is a function of t, so we should be all the way into t's, but it is not necessary. If you were to go all the way, you could say, or dz dt is equal to, in parentheses, y is sine of t minus 2x will give me minus 6t squared plus 2 times 6t plus, in parentheses, x is 3t squared plus 1 minus 2y, so that's minus 2 sine of t, all times cosine of t. It doesn't make it look any better, really. It's just fewer variables, okay? But either answer is technically acceptable. Here's what's not acceptable. Do not avoid the chain rule. In other words, don't sub x and y into z and then take the derivative. That would be avoiding the chain rule. Okay? All right, let's try another one. In this next one, we're going to have to calculate a few more things because we're being asked to find del z, del s, and del z, del t. So I'm going to write those out, and then we're going to calculate all the derivatives that we need, and then we'll plop them in. Okay, so this looks like z is a function of x and y, x is a function of s and t, and y is a function of s and t. So del z, del s is going to be a sum of the branches, okay? We'll have to start down the x branch, so we'll get del z, del x, and then on the x branch we go down to s, so we need a del x, del s. Then we add the second branch, going down y, we get del z, del y. From y to s, we get del y, del s. And then del z, del t is similar, where you go down the x and the y branches. Down x, we get del z, del x, and then down to t, we get del x, del t, plus, now down the y branch, we have del z, del y. From y to t, we have del y, del t. Okay, now let's get all of our parts. Del z, my dels are getting sloppier and sloppier. Del z, del x is equal to, and now I'm going to run, well, hey, looks like these are the same function as before, so I already have these. It's negative 2x plus y. Del z, del y is equal to x minus 2y. Okay. Then we have, and you know what, I'm going to move this one over to the bottom. I'm going to do all my x stuff in a row and then all my y stuff in a row. Okay. So I've got del z, del x. I'm going to find del x, del s first. That will be, okay, if x is t squared, the derivative with respect to s is 0 there. Derivative of st with respect to s is going to be t, and derivative of 1 is 0. So del x, del s is just t. Del x, del t is going to be 2t plus s. Okay, those are all my x derivatives. Now I want my y derivatives. I need del y, del s. Y is e to the st, so the derivative of y with respect to s is e to the st times the derivative of st with respect to s, which gives us a t in front. Del y, del t is also going to be e to the st, but then times the derivative with respect to t of st, which gives me an s out in front. Okay, I have my parts. I'm going to plug them in. So we have del z, del s equals del z, del x. So that's going to be my y minus 2x times del x, del s, that's t, plus del z, del y, that's x minus 2y, times del y, del s, that's t e to the st. Done. Okay. Del z, del t. I'm looking at my formula there. I've got del z, del x, which is going to be y minus 2x, times del x, del t, which is 2t plus s, plus del z, del y, which is x minus 2y, times del y, del t, which is s e to the st. These are my final answers. I'm not going to mess with them anymore. There's really no need, right? So what we would be interested in with these is like actually knowing some x, y, t, and s values and calculating a numerical value for the change in z with respect to s or the change in z with respect to t.